Cloud computing, also known as on-demand computing, is a kind of internet-based computing, where shared resources, data and information are provided to computers and other devices on demand. It is a model for enabling ubiquitous, on-demand access to a shared pool of configurable computing resources. Cloud computing and storage solutions provide users and enterprises with various capabilities to store and process their data in third-party data centers. It relies on sharing of resources to achieve coherence and economies of scale, similar to a utility over a network. At the foundation of cloud computing is the broader concept of converged infrastructure and shared services. Cloud computing is a model for enabling ubiquitous, convenient, on-demand network access to a shared pool of configurable computing resources that can be rapidly provisioned and released with minimal management effort. Cloud computing, or in simplest shorthand just the cloud, also focuses on maximizing the effectiveness of the shared resources. Cloud resources are usually not only shared by multiple users but are also dynamically reallocated per demand. This can work for allocating resources to users. For example, a cloud computer facility that serves European users during European business hours with a specific application may reallocate the same resources to serve North American users during North America's business hours with a different application. This approach helps maximize the use of computing power while reducing the overall cost of resources by using less power, air conditioning, rack space, etc. to maintain the system. With cloud computing, multiple users can access a single server to retrieve and update their data without purchasing licenses for different applications. The term moving to cloud also refers to an organization moving away from a traditional CAPEX model to the OPEX model. Proponents claim that cloud computing allows companies to avoid upfront infrastructure costs, and focus on projects that differentiate their businesses instead of on infrastructure. Proponents also claim that cloud computing allows enterprises to get their applications up and running faster, with improved manageability and less maintenance, and enables IT to more rapidly adjust resources to meet fluctuating and unpredictable business demand. Cloud providers typically use a pay-as-you-go model. This can lead to unexpectedly high charges if administrators do not adapt to the cloud pricing model. The present availability of high-capacity networks, low-cost computers and storage devices as well as the widespread adoption of hardware virtualization, service-oriented architecture, and autonomic and utility computing have led to a growth in cloud computing. Companies can scale up as computing needs increase and then scale down again as demands decrease. Cloud computing has now become a highly demanded service or utility due to the advantages of high computing power, cheap cost of services, high performance, scalability, accessibility as well as availability. Cloud vendors are experiencing growth rates of 50% per annum. But due to being in a stage of infancy, it still has some pitfalls which need to be given proper attention to make cloud computing services more reliable and user-friendly. History of cloud computing. Origin of the term equals, the origin of the term cloud computing is unclear. The word cloud is commonly used in science to describe a large agglomeration of objects that visually appear from a distance as a cloud and describes any set of things whose details are not inspected further in a given context. Another explanation is that the old programs that drew network schematics surrounded the icons for servers with a circle, and a cluster of servers in a network diagram had several overlapping circles, which resembled a cloud. In analogy to above usage, the word cloud was used as a metaphor for the Internet, and a standardized cloud-like shape was used to denote a network on telephony schematics and later to depict the Internet and computer network diagrams. With this simplification, the implication is that the specifics of how the endpoints of a network are connected are not relevant for the purposes of understanding the diagram. The cloud symbol was used to represent networks of computing equipment in the original ARPANET by as early as 1977, and the CSNET by 1981, both predecessors to the Internet itself. The term cloud has been used to refer to platforms for distributed computing. In Wired's April 1994 feature Bill and Andy's Excellent Adventure 2 on the Apple spin-off General Magic, Andy Hesselt comments on General Magic's distributed programming language Telescript that the beauty of Telescript is that now, instead of just having a device to program, we now have the entire cloud out there, where a single program can go and travel to many different sources of information and create sort of a virtual service. No one had conceived that before. The example Jim White, the designer of Telescript, X400 and ASN1, uses now is a data ranging service where a software agent goes to the flower store and orders flowers and then goes to the ticket shop and gets the tickets for the show, and everything is communicated to both parties. References to cloud computing in its modern sense appeared as early as 1996, with the earliest known mention in a Compaq internal document. The popularization of the term can be traced to 2006 when Amazon.com introduced the Elastic Compute Cloud. The 1970s during the mid-1970s, time-sharing was popularly known as a JE. This terminology was mostly associated with large vendors such as IBM and DEC. IBM developed the VM operating system to provide time-sharing services via virtual machines. The 1990s in the 1990s, telecommunications companies, who previously offered primarily dedicated point-to-point data circuits, began offering virtual private network services with comparable quality of service, but at a lower cost. By switching traffic as they saw fit to balance server use, they could use overall network bandwidth more effectively. They began to use the cloud symbol to denote the demarcation point between what the provider was responsible for and what users were responsible for. Cloud computing extends this boundary to cover all servers as well as the network infrastructure. As computers became more prevalent, scientists and technologists explored ways to make large-scale computing power available to more users through time-sharing. They experimented with algorithms to optimize the infrastructure, platform, and applications to prioritize CPUs and increase efficiency for end users. The new millennium, 2000s. Since 2000, cloud computing has come into existence. In early 2008, NASA's Open Nebula, enhanced in the Reservoir European Commission-funded project, became the first open-source software for deploying private and hybrid clouds, and for the Federation of Clouds. In the same year, efforts were focused on providing quality of service guarantees to cloud-based infrastructures, in the framework of the IRMOS European Commission-funded project, resulting in a real-time cloud environment. By mid-2008, Gartner saw an opportunity for cloud computing to shape the relationship among consumers of IT services, those who use IT services and those who sell them, and observed that organizations are switching from company-owned hardware and software assets to per-use service-based models so that the projected shift to computing will result in dramatic growth in IT products in some areas and significant reductions in other areas. Microsoft Azure was announced as Azure in October 2008 and released on February 1, 2010 as Windows Azure, before being renamed to Microsoft Azure on March 25, 2014. In July 2010, Rackspace Hosting and NASA jointly launched an open-source cloud software initiative known as Openstack. The Openstack project intended to help organizations offer cloud computing services running on standard hardware. The early code came from NASA's Nebula platform as well as from Rackspace's Cloud Files platform. On March 1, 2011, IBM announced the IBM Smart Cloud Framework to support Smarter Planet. Among the various components of the Smarter Computing Foundation, cloud computing is a critical piece. On June 7, 2012, Oracle announced the Oracle Cloud. While aspects of the Oracle Cloud are still in development, this cloud offering is poised to be the first to provide users with access to an integrated set of IT solutions, including the applications, platform, and infrastructure layers. Similar concepts, cloud computing is the result of the evolution and adoption of existing technologies and paradigms. The goal of cloud computing is to allow users to take IT from all of these technologies, without the need for deep knowledge about or expertise with each one of them. The cloud aims to cut costs, and helps the users focus on their core business instead of being impeded by IT obstacles. The main enabling technology for cloud computing is virtualization. Virtualization software separates a physical computing device into one or more virtual devices, each of which can be easily used and managed to perform computing tasks. With operating system level virtualization essentially creating a scalable system of multiple independent computing devices, idle computing resources can be allocated and used more efficiently. Virtualization provides the agility required to speed up IT operations, and reduces cost by increasing infrastructure utilization. Autonomic computing automates the process through which the user can provision resources on demand. By minimizing user involvement, automation speeds up the process, reduces labor costs and reduces the possibility of human errors. Users routinely face difficult business problems. Cloud computing adopts concepts from service-oriented architecture that can help the user break these problems into services that can be integrated to provide a solution. Cloud computing provides all of its resources as services, and makes use of the well-established standards and best practices gained in the domain of SOA to allow global and easy access to cloud services in a standardized way. Cloud computing also leverages concepts from utility computing to provide metrics for the services used. Such metrics are at the core of the public cloud pay-per-use models. In addition, measured services are an essential part of the feedback loop in autonomic computing, allowing services to scale on demand and to perform automatic failure recovery. Cloud computing is a kind of grid computing. It has evolved by addressing the coercion and reliability problems. Cloud computing provides the tools and technologies to build data compute-intensive parallel applications with much more affordable prices compared to traditional parallel computing techniques. Cloud computing shares characteristics with client-to-server model. Client-to-server computing refers broadly to any distributed application that distinguishes between service providers and service requesters. Grid computing a form of distributed and parallel computing, whereby a super and virtual computer is composed of a cluster of networked, loosely coupled computers acting in concert to perform very large tasks. Mainframe computer powerful computers used mainly by large organizations for critical applications, typically bulk data processing such as census, industry and consumer statistics, police and secret intelligence services, enterprise resource planning, and financial transaction processing. Utility computing the packaging of computing resources, such as computation and storage, as a metered service similar to a traditional public utility, such as electricity. Peer-to-peer a distributed architecture without the need for central coordination. Participants are both suppliers and consumers of resources. Characteristics: cloud computing exhibits the following key characteristics. Agility improves with users' ability to re-provision technological infrastructure resources. WTF? Cost reductions claimed by cloud providers. A public cloud delivery model converts capital expenditure to operational expenditure. This purportedly lowers barriers to entry, as infrastructure is typically provided by a third party and does not need to be purchased for one-time or infrequent intensive computing tasks. Pricing on a utility computing basis is fine-grained, with usage-based options and fewer IT skills are required for implementation. The eFiscal project's state-of-the-art repository contains several articles looking into cost aspects in more detail, most of them concluding that cost savings depend on the type of activities supported and the type of infrastructure available in-house. Device and location independence enable users to access systems using a web browser regardless of their location or what device they use. As infrastructure is off-site and accessed via the Internet, users can connect from anywhere. Maintenance of cloud computing applications is easier, because they do not need to be installed on each user's computer and can be accessed from different places. Multi-tenancy enables sharing of resources and costs across a large pool of users, thus allowing for centralization of infrastructure in locations with lower costs, peak load capacity increases, utilization and efficiency improvements for systems that are often only 10–20% utilized. Performance is monitored, and consistent and loosely coupled architectures are constructed using web services as the system interface. Productivity may be increased when multiple users can work on the same data simultaneously, rather than waiting for it to be saved and emailed. Time may be saved as information does not need to be re-entered when fields are matched, nor do users need to install application software upgrades to their computer. Reliability improves with the use of multiple redundant sites, which makes well-designed cloud computing suitable for business continuity and disaster recovery. Scalability and elasticity via dynamic provisioning of resources on a fine-grained, self-service basis in near real time, without users having to engineer for peak loads. This gives the ability to scale up when the usage need increases or down if resources are not being used. Security can improve due to centralization of data, increased security-focused resources, etc., but concerns can persist about loss of control over certain sensitive data, and the lack of security for stored kernels. Security is often as good as or better than other traditional systems, in part because providers are able to devote resources to solving security issues that many customers cannot afford to tackle. However, the complexity of security is greatly increased when data is distributed over a wider area or over a greater number of devices, as well as in multi-tenant systems shared by unrelated users. In addition, user access to security audit logs may be difficult or impossible. Private cloud installations are in part motivated by users' desire to retain control over the infrastructure and avoid losing control of information security. The National Institute of Standards and Technology's definition of cloud computing identifies 5 essential characteristics. On-demand self-service. A consumer can unilaterally provision computing capabilities, such as server time and network storage, as needed automatically without requiring human interaction with each service provider. Broad network access. Capabilities are available over the network and accessed through standard mechanisms that promote use by heterogeneous thin or thick client platforms. Resource pooling. The provider's computing resources are pooled to serve multiple consumers using a multi-tenant model, with different physical and virtual resources dynamically assigned and reassigned according to consumer demand. Rapid elasticity. Capabilities can be elastically provisioned and released, in some cases automatically, to scale rapidly outward and inward commensurate with demand. To the consumer, the capabilities available for provisioning often appear unlimited and can be appropriated in any quantity at any time. Measured service. Cloud systems automatically control and optimize resource use by leveraging a metering capability at some level of abstraction appropriate to the type of service. Resource usage can be monitored, controlled, and reported, providing transparency for both the provider and consumer of the utilized service. Service models. Though service-oriented architecture advocates everything as a service, cloud computing providers offer their services according to different models, which happen to form a stack: infrastructure, platform and software as a service. Infrastructure as a service equals. In the most basic cloud service model, and according to the IETF, providers of IaaS offer computers physical or virtual machines and other resources. IaaS refers to online services that abstract user from the detail of infrastructure like physical computing resources, location, data partitioning, scaling, security, backup etc. A hypervisor, such as Xen, Oracle VirtualBox, KVM, VMware ESXi, or Hyper-V runs the virtual machines as guests. Pools of hypervisors within the cloud operational system can support large numbers of virtual machines and the ability to scale services up and down according to customers' varying requirements. IaaS clouds often offer additional resources such as a virtual machine disk image library, raw block storage, file or object storage, firewalls, load balancers, IP addresses, virtual local area networks, and software bundles. IaaS cloud providers supply these resources on demand from their large pools of equipment installed in data centers. For wide area connectivity, customers can use either the Internet or carrier clouds. To deploy their applications, Cloud users install operating system images and their application software on the cloud infrastructure. In this model, the cloud user patches and maintains the operating systems and the application software. Cloud providers typically bill IaaS services on a utility computing basis. Cost reflects the amount of resources allocated and consumed. Platform as a service equals. PaaS vendors offers a development environment to application developers. The provider typically develops toolkit and standards for development and channels for distribution and payment. In the PaaS models, cloud providers deliver a computing platform, typically including operating system, programming language execution environment, database, and web server. Application developers can develop and run their software solutions on a cloud platform without the cost and complexity of buying and managing the underlying hardware and software layers. With some PaaS offers like Microsoft Azure and Google App Engine, the underlying computer and storage resources scale automatically to match application demands so that the cloud user does not have to allocate resources manually. The latter has also been proposed by an architecture aiming to facilitate real-time in cloud environments. Even more specific application types can be provided via PaaS, such as media encoding as provided by services like Bitcoin.com or Media.io. Some integration and data management providers have also embraced specialized applications of PaaS as delivery models for data solutions. Examples include IPaaS and DPaaS. IPaaS enables customers to develop, execute and govern integration flows. Under the IPaaS integration model, customers drive the development and deployment of integrations without installing or managing any hardware or middleware. DPaaS delivers integration and data management products as a fully managed service. Under the DPaaS model, the PaaS provider, not the customer, manages the development and execution of data solutions by building tailored data applications for the customer. DPaaS users retain transparency and control over data through data visualization tools. Platform as a service. The consumer does not manage or control the underlying cloud infrastructure including network, servers, operating systems, or storage, but has control over the deployed applications and possibly configuration settings for the application hosting environment. Software as a service equals. In the software as a service model, users gain access to application software and databases. Cloud providers manage the infrastructure and platforms that run the applications. SaaS is sometimes referred to as on-demand software, and is usually priced on a pay-per-use basis or using a subscription fee. In the SaaS model, cloud providers install and operate application software in the cloud and cloud users access the software from cloud clients. Cloud users do not manage the cloud infrastructure and platform where the application runs. This eliminates the need to install and run the application on the cloud user's own computers, which simplifies maintenance and support. Cloud applications differ from other applications in their scalability, which can be achieved by cloning tasks onto multiple virtual machines at runtime to meet changing work demand. Load balancers distribute the work over the set of virtual machines. This process is transparent to the cloud user, who sees only a single access point. To accommodate a large number of cloud users, cloud applications can be multi-tenant, meaning that any machine may serve more than one cloud user organization. The pricing model for SaaS applications is typically a monthly or yearly flat fee per user, so prices become scalable and adjustable if users are added or removed at any point. Proponents claim that SaaS gives a business the potential to reduce IT operational costs by outsourcing hardware and software maintenance and support to the cloud provider. This enables the business to reallocate IT operations costs away from hardware-software spending and from personnel expenses, towards meeting other goals. In addition, with applications hosted centrally, updates can be released without the need for users to install new software. One drawback of SaaS comes with storing the user's data on the cloud provider's server. As a result, there could be unauthorized access to the data. For this reason, Users are increasingly adopting intelligent third-party key management systems to help secure their data. Software as a service known as on-demand software, it provides the software service to the consumer hosted on cloud. Cloud clients. Users access cloud computing using networked client devices, such as desktop computers, laptops, tablets and smartphones, and any Ethernet-enabled device such as home automation gadgets. Some of these devices are cloud clients rely on cloud computing for all or a majority of their applications so as to be essentially useless without it. Examples are thin clients and the browser-based Chromebook. Many cloud applications do not require specific software on the client and instead use a web browser to interact with a cloud application. With Ajax and HTML5, these web user interfaces can achieve a similar, or even better, look and feel to native applications. Some cloud applications, however, support specific client software dedicated to these applications. Some legacy applications are delivered via a screen-sharing technology. Deployment models. Private cloud Private cloud is cloud infrastructure operated solely for a single organization, whether managed internally or by a third party, and hosted either internally or externally. Undertaking a private cloud project requires a significant level and degree of engagement to virtualize the business environment, and requires the organization to re-evaluate decisions about existing resources. When done right, it can improve business, but every step in the project raises security issues that must be addressed to prevent serious vulnerabilities. Self-run data centers are generally capital-intensive. They have a significant physical footprint, requiring allocations of space, hardware, and environmental controls. These assets have to be refreshed periodically, resulting in additional capital expenditures. They have attracted criticism because users still have to buy, build, and manage them, and thus do not benefit from less hands-on management, essentially, lacking the economic model that makes cloud computing such an intriguing concept. Public cloud A cloud is called a public cloud, when the services are rendered over a network that is open for public use. Public cloud services may be free. Technically there may be little or no difference between public and private cloud architecture, however, security consideration may be substantially different for services that are made available by a service provider for a public audience and when communication is effected over a non-trusted network. Generally, public cloud service providers like Amazon AWS, Microsoft and Google own and operate the infrastructure at their data center and access is generally via the Internet. AWS and Microsoft also offer Direct Connect services called AWS Direct Connect and Azure Express Route respectively. Such connections require customers to purchase or lease a private connection to a peering point offered by the cloud provider. Hybrid cloud Hybrid cloud is a composition of two or more clouds that remain distinct entities but are bound together, offering the benefits of multiple deployment models. Hybrid cloud can also mean the ability to connect colocation, managed and/or dedicated services with cloud resources. Gartner, Incorporated defines a hybrid cloud service as a cloud computing service that is composed of some combination of private, public and community cloud services, from different service providers. A hybrid cloud service crosses isolation and provider boundaries so that it can't be simply put in one category of private, public, or community cloud service. It allows one to extend either the capacity or the capability of a cloud service, by aggregation, integration or customization with another cloud service. Varied use cases for hybrid cloud composition exist. For example, an organization may store sensitive client data in-house on a private cloud application, but interconnect that application to a business intelligence application provided on a public cloud as a software service. This example of hybrid cloud extends the capabilities of the enterprise to deliver a specific business service through the addition of externally available public cloud services. Hybrid cloud adoption depends on a number of factors such as data security and compliance requirements, level of control needed over data, and the applications an organization uses. Another example of hybrid cloud is one where IT organizations use public cloud computing resources to meet temporary capacity needs that cannot be met by the private cloud. This capability enables hybrid clouds to employ cloud bursting for scaling across clouds. Cloud bursting is an application deployment model in which an application runs in a private cloud or data center and bursts to a public cloud when the demand for computing capacity increases. A primary advantage of cloud bursting and a hybrid cloud model is that an organization only pays for extra compute resources when they are needed. Cloud bursting enables data centers to create an in-house IT infrastructure that supports average workloads, and use cloud resources from public or private clouds, during spikes in processing demands. The specialized model of hybrid cloud, which is built atop heterogeneous hardware, is called cross-platform hybrid cloud. A cross-platform hybrid cloud is usually powered by different CPU architectures, for example, x86-64 and ARM, underneath. Users can transparently deploy and scale applications without knowledge of the cloud's hardware diversity. This kind of cloud emerges from the rise of ARM-based system-on-chip for server-class computing. Others. Community cloud. Community cloud shares infrastructure between several organizations from a specific community with common concerns, whether managed internally or by a third party, and either hosted internally or externally. The costs are spread over fewer users than a public cloud, so only some of the cost savings potential of cloud computing are realized. Distributed cloud. A cloud computing platform can be assembled from a distributed set of machines in different locations, connected to a single network or hub service. It is possible to distinguish between two types of distributed clouds, public resource computing and volunteer cloud. Public resource computing. This type of distributed cloud results from an expansive definition of cloud computing, because they are more akin to distributed computing than cloud computing. Nonetheless, it is considered a subclass of cloud computing, and some examples include distributed computing platforms such as BOINC and Folding at Home. Volunteer cloud. Volunteer cloud computing is characterized as the intersection of public resource computing and cloud computing, where a cloud computing infrastructure is built using volunteered resources. Many challenges arise from this type of infrastructure, because of the volatility of the resources used to build it and the dynamic environment it operates in. It can also be called peer-to-peer clouds, or ad hoc clouds. An interesting effort in such direction is Cloud at Home. It aims to implement a cloud computing infrastructure using volunteered resources, providing a business model to incentivize contributions through financial restitution. Intercloud. The Intercloud is an interconnected global cloud of clouds, and an extension of the Internet network of networks on which it is based. The focus is on direct interoperability between public cloud service providers, more so than between providers and consumers. Multi-cloud. Multi-cloud is the use of multiple cloud computing services in a single heterogeneous architecture to reduce reliance on single vendors, increase flexibility through choice, mitigate against disasters, etc. It differs from hybrid cloud in that it refers to multiple cloud services, rather than multiple deployment modes. Architecture. Cloud architecture, the systems architecture of the software systems involved in the delivery of cloud computing, typically involves multiple cloud components communicating with each other over a loose coupling mechanism such as a messaging queue. Elastic provision implies intelligence in the use of tight or loose coupling as applied to mechanisms such as these and others. Cloud engineering. Cloud engineering is the application of engineering disciplines to cloud computing. It brings a systematic approach to the high-level concerns of commercialization, standardization, and governance in conceiving, developing, operating and maintaining cloud computing systems. It is a multidisciplinary method encompassing contributions from diverse areas such as systems, software, web, performance, information, security, platform, risk, and quality engineering. Security and privacy. Cloud computing poses privacy concerns because the service provider can access the data that is in the cloud at any time. It could accidentally or deliberately alter or even delete information. Many cloud providers can share information with third parties if necessary for purposes of law and order, even without a warrant. That is permitted in their privacy policies, which users have to agree to before they start using cloud services. Solutions to privacy include policy and legislation, as well as end users' choices for how data is stored. Users can encrypt data that is processed or stored within the cloud to prevent unauthorized access. According to the Cloud Security Alliance, the top 3 threats in the cloud are insecure interfaces and APIs, data loss and leakage, and hardware failure, which accounted for 29%, 25% and 10% of all cloud security outages respectively. Together these form shared technology vulnerabilities. In a cloud provider platform being shared by different users, there may be a possibility that information belonging to different customers resides on same data server. Therefore, information leakage may arise by mistake when information for one customer is given to other. Additionally, Eugene Schultz, Chief Technology Officer at Imagined Security, said that hackers are spending substantial time and effort looking for ways to penetrate the cloud. There are some real Achilles heels in the cloud infrastructure that are making big holes for the bad guys to get into. Because data from hundreds or thousands of companies can be stored on large cloud servers, hackers can theoretically gain control of huge stores of information through a single attack, a process he called hyperjacking. Some examples of this include the Dropbox security breach, and iCloud 2014 leak. Dropbox had been breached in October 2014, having over 7 million of its users' passwords stolen by hackers in an effort to get monetary value from it by bitcoins. By having these passwords, they are able to read private data as well as have this data be indexed by search engines. There is the problem of legal ownership of the data. Many terms of service agreements are silent on the question of ownership. Physical control of the computer equipment is more secure than having the equipment off-site and under someone else's control. This delivers great incentive to public cloud computing service providers to prioritize building and maintaining strong management of secure services. Some small businesses that don't have expertise in IT security could find that it's more secure for them to use a public cloud. There is the risk that end users don't understand the issues involved when signing on to a cloud service. This is important now that cloud computing is becoming popular and required for some services to work, for example for an intelligent personal assistant. Fundamentally, private cloud is seen as more secure with higher levels of control for the owner. However, public cloud is seen to be more flexible and requires less time and money investment from the user. The future, cloud computing is therefore still as much a research topic, as it is a market offering. What is clear through the evolution of cloud computing services is that the CTO is a major driving force behind cloud adoption. The major cloud technology developers continue to invest billions a year in cloud R&D. For example, in 2011 Microsoft committed 90% of its $9.6 billion R&D budget to cloud. Central partners also predict that SaaS revenue will be growing from $13.5 billion in 2011 to $32.8 billion in 2016. Additionally, more industries are turning to cloud technology as an efficient way to improve quality services due to its capabilities to reduce overhead costs, downtime, and automate infrastructure deployment. See also. References. Further reading, Millard, Christopher. Cloud Computing Law. Oxford University Press. ISBN 978-0-19-967168-7. Singh, Jatinder. Powles, Julia. Pasquia, Thomas. Bacon, Jean. Data Flow Management and Compliance in Cloud Computing. IEEE Cloud Computing 2, 24 €32 doi, 10.1109/MCC. 2015.69. Armrest, Michael. Stoica, Ion. Zahariah, Matthew. Fox, Armando. Griffith, Reen. Joseph, Anthony D. Katz, Randy. Koninsky, Andy. Lee, Gunhu. Patterson, David. Rabkin, Ariel. A view of cloud computing. Communications of the ACM 53, 50 DOI, 10.1145/1,721,654.17216772. Hu, Tung Hui. A Prehistory of the Cloud. MIT Press. ISBN 978-0-262-02951-3. Mel, P. The NIST Definition of Cloud Computing. Retrieved November 1, 2015, from National Institute of Standards and Technology website, https://nist.gov/NIST/BUBS 800-145 PDF. External links, Evolution of as-a-Service Era in Cloud. A Review on as-a-Service Framework, 2015. Above the Clouds, A Berkeley View of Cloud Computing, Technical Report No. UCBEECS 2009-28, February 10, 2009, http www.eexberkeleyedutech.pts 2009-28 html